Right. I think I could say that it's probably my favorite portion of the course. Numerical equation, quite a lot of research has been oriented around it. Having spent the last week on numerical differentiation, now we're going to consider the opposite problems. Some of the same ideas apply because of a heavy reliance on polynomial interpolation. Okay, so the problem that we want to solve is very simple to state. What we're trying to do is approximate the definite integral of some given function f(x) on some given interval ab. Now, so why numerical integration is necessary? Because you've all taken calculus too. I'll learn various integration rules, and there's software out there that implements those integration rules, and other ones that are to advance for Cal 2. For one thing, numerical integration is a lot more efficient than software carrying out symbolic integration. Dr. Cole at the Coast, her research is about the symbolic integration. Now, yes, you are giving up getting an exact answer, but you can get a highly accurate approximation of many different integrals, generally speaking, than in a whole lot less time. So the extra computational expense that would be needed to get an exact result isn't really worth it. Also, some integrals, even ones that appear have a very simple appearance, cannot be worked out using kind of integration rules that we learned. One example that actually does come up in calculus is arc length of a curve. So the arc length of a curve, what is described by the equation y equals f of x, given by this formula here. I remember covering this formula in Cal 3. Now, what happens is, in most cases, whatever f of x is, this kind of integrand would be very difficult to handle. And it's actually kind of amusing to see the lengths that calculus textbooks will go to come up with contrived curves for which this integral can be done using whatever algebraic hocus pocus. It's kind of ridiculous at times. But for general purpose, this integral often needs to be handled numerically. Here's another example, a Gaussian function. And you can integrate e to the minus x easily, but e to the minus x squared, forget about it. It's been proven that there's no antiderivative of e to the minus x squared in terms of elementary functions. And this function the Gaussian function is quite important in like statistics and differential equations. So it's unfortunate that we have no way of evaluating this exactly. It must be done numerically. That's another reason. Yet another reason why symbolic integration is not practical. What if we don't even have f of x? The same question came up with differentiation. We might only know f of x at select points, and we still want to try to approximate the area under a curve as best we can. So how are we going to proceed? What we use is called a quadrature rule. So the integral is approximated by a summation of values of your integrand at select x values. Those are called the nodes of a quadrature rule, and they're multiplied by these numbers w sub I, and those are called weights. So So once you have the nodes and the weights, that completely specifies the quadrature rule. And then there would be some error in that approximation. Now, even if you haven't seen quadrature rules before, in a way you actually have, just they might not have been referred to by that name. So this summation right here, so sum of f values multiplied by these weights. Did anyone tell me what they've seen from calculus 2 that this might remind you of? When dealing with approximate intervals.
Riemann sum?
Yes. A Riemann sum actually is a form of quadrature rule. It's not a very accurate one, as we'll see, but yeah, because a Riemann sum is a sum of f values, so multiplied by certain quantity, that would be like a difference in x values, so when you were evaluating a Riemann sum, you were approximating the area under a curve by summing up the areas of rectangles. So the f values, f of xi, would be the heights of each rectangle, and whatever it's multiplied by, that would represent the width. That's why it makes sense to call this a quadrature rule, because what you're doing, you're approximating the area under a curve by summing the areas of quadrilaterals. Now, when you learned about Riemann sums in Cal 2, you were probably given homework problems where you had to compute the value of the Riemann sum for a certain number of rectangles, and also take the limit as the number of rectangles went to infinity, and obtain the exact result. Here, we actually want to minimize the number of nodes, because this kind of approximation, there's a certain computational expense in evaluating this. The main expense is from evaluating the function f, your integrand. So we want to try to obtain high accuracy, highly accurate approximation of the integral without going to too much computational expense from needless evaluations of f. So that's our goal. We want high accuracy, but the number of nodes n to be small. So unfortunately, those criteria are competing against each other. But as we go through this chapter, we'll learn about ways to obtain very high accuracy with fewer nodes. So spoiler number 1, don't bother with a Riemann sum. It's literally the worst quadrature rule that I know. Okay. Well, okay. When you took Cal 2, if you have to work out problems about Riemann sums, there are 3 different types of Riemann sums. That were based on where you evaluated your integrand. Do you remember what those were? The 3 different types of Riemann sums?
Left, right, and then like a midpoint one, wasn't there?
Yeah, left endpoint, right endpoint, and midpoint. Midpoint's actually pretty good. Left endpoint, right endpoint are actually so bad we're not even going to talk about them. Okay. But we will see the midpoint rule later. Okay. So the issue here is, how should we choose nodes and weights so that we get most bang for our buck? So highest accuracy, ideal combination of accuracy and efficiency. So to answer these questions, we pose 2 new ones. What kind of functions are easy to integrate? And once we establish that, how can we integrate a approximate integrated general function by using by relating it to functions for which integrals are easy? Okay. So, what about these questions? What kind of functions are particularly easy to integrate?
Quadratics.
Okay, yes, they certainly are. Or a little more generally, yes, polynomials. Okay. So now if we have a general function f of x, if f of x is allowed to be anything, how can we get an approximate integral of f using the fact that polynomials are easily integrated?
Interpolation.
Yeah, interpolation. And that leads to what is called interpolatory quadrature. So the idea is we approximate the integral of f by computing the polynomial p sub n minus 1. The subscript of n minus 1 is because we're going to use our nodes, whatever these nodes are, as our n interpolation points. And remember, the degree of the interpolant is always one less than the number of interpolation points you have. Okay, so the approximation of the integral is going to be obtained by the exact integral of the approximation of our integrand. Now, let's take a look at what happens when we write the interpolating polynomial in Lagrange form. So our true integral is approximated by the integral of our interpolant. Then we write the interpolant in Lagrange form right here. So it's the sum of the values of f at our interpolation points times the Lagrange polynomials. But then what we do is we use the linearity of the integral and we pull out the summation, and we also pull out f of xi because this isn't f of x, it's f of xi. We're integrating with respect to x. So any quantity that does not depend on x is a constant. So it can be pulled out of the integral. So now we have the sum of f values times these quantities here, which are the integrals of our Lagrange polynomials. So we can conclude from that the weights, when you're carrying out interpolatory quadrature in particular, the weights are just the integrals of the Lagrange polynomials. Questions so far about interpolatory quadrature? Yes.
Now, do we need to stick to Lagrange interpolation? What's just the very basic case?
Okay. You mean like Lagrange as opposed to other types of interpolation? Okay. Okay, I'm not sure if your question is about the form of the interpolants, or like Lagrange versus Newton versus. Or,
Yes, I would say yes. The form.
okay. Reason why we use Lagrange here, even though polynomial is the same, is so that our approximation will have this form of sum of f values times weights. And since the Lagrange form is the only one that has the values of f at the nodes as coefficients, that's why Lagrange makes sense. Or because if we use, for example, power form, so using a van der Waals matrix, then okay, we'd have integrals of our monomials here. Then we have very complicated expressions here that would involve the f values, but it'd be a mess. But there are other forms of interpolation that could be used. Later in this chapter, we'll see how Hermite can come in handy. One can also use what's called, I haven't talked about it in this class, but trigonometric interpolation, representing a function as a combination of sines and cosines, because those also could be integrated. Okay. Which actually relates to Chebyshev polynomials. polynomials, because those could be represented as cosines. Okay. Other questions? Now, I want to draw a parallel between what I've just shown you about these quadrature weights and what we saw in numerical differentiation. When you're deriving finite difference formulas by for derivatives, by computing the derivatives of Lagrange polynomials and evaluating them in x naught. So the parallel here is that we have these problems, differentiation and integration, that both can be solved most easily for polynomials. And in both cases, we want an approximation that is a linear combination of values of your f. In both cases, the way you get the coefficient is you solve your original problem on the Lagrange polynomials. So for integration, we integrate the Lagrange polynomials. For derivative at x naught, we take the derivative of Lagrange polynomials at x naught. So anytime you're trying to solve some problem for some function f, you can approximately solve it by, and you want an approximation as a linear combination of f values, then the coefficients in your linear combination would be that problem solved for Lagrange. Okay. One important piece of terminology here, the degree of accuracy. And so when we're dealing with interpolatory quadrature rules, the degree of accuracy is the highest degree of polynomial that will be integrated exactly by your quadrature rule. Now this is going to vary from rule to rule, but what we can say in general is that anytime you have an interpolatory quadrature rule that has n nodes, you're going to be approximating f by a polynomial of degree n minus 1. So that's going to be evaluated exactly. So if your interpolatory quadrature rule has n nodes, the degree of accuracy will be at least n minus 1. So that's a lower bound on degree of accuracy. But we'll see some examples where it could be exceeded. Very important point that'll come back to haunt us later. Ideally, the weights of any quadrature rule ought to be positive. Makes sense. Think of your simplest quadrature rule, Riemann sum. The weights in that case represent the width of a rectangle. Those are so obviously positive. The examples I'll show you today will have positive weights, but there will be some cases, if you're not careful, where you can get negative weights, and then you can likely get very bad results. So this point ought to be emphasized that we can't always take for granted that any other quadrature rule will have positive weights. So ones that do is a good telling. Now, before I get to specific examples of quadrature rules, or the interpolatory quadrature rules, we'll make a comment about sensitivity, because we talked about sensitivity last time with numerical differentiation. It was found on a simple example that the problem of numerical differentiation tends to be ill conditioned, that the error increases as the spacing h goes to 0. So what about numerical integration? So here, backward error analysis comes into play again. So remember, backward error analysis, your approximate solution is the exact solution of a nearby problem in some sense. That's exactly what we're doing here, and we're doing it with differentiation too. Your approximate integral or approximate derivative is the exact integral derivative of an interpolating polynomial that's meant to approximate your f of x. So this problem is very well suited for backward error analysis. So here, the forward error is just, so let's suppose this is your exact integrand, and this is your approximate integrand that you're integrating exactly, like your interpolating polynomial. Now, so a forward error is just the integral, so the exact integral minus the approximate integral. The backward error is the absolute backward error. That is the, here we look at the error in your approximation of f. So, for example, this would be the maximum error in approximating f on the interval AB. So now we can use forward and backward error to estimate the condition number. So the absolute condition number would be the absolute forward error divided by the absolute backward error in absolute value. That's a lot of absolutes. So the forward error, we fill in what that is. So that's the absolute value of the difference in integrals. And then we divide that by the maximum error in our approximation of f. Now, the absolute value of an integral, this is a good thing to, well, it's good to know things, is always less than or equal to the integral of the absolute value of the integrand. So you can, if you have the absolute value of the integral, you can move the absolute value bars inside as long as it's less than or equal to. But then, the integral of this absolute value, that is less than or equal to the length of the interval AB times the maximum value of the integrand, which is absolute value of f minus fn. But then, these cancel. So we can say that the absolute condition number is less than or equal to b minus a, which is the interval. So that's quite nice, because it means that the problem of numerical integration is a well-conditioned problem, which isn't really surprising considering that we found differentiation to be ill-conditioned. So remember that in chapter 2, we saw that we can approximate a condition number by a derivative. In fact, the estimate for the absolute condition number is a derivative of whatever it is you're computing. Now, differentiation and integration, of course, are inverse processes of each other. And I don't know if it even gets covered in Cal 2 anymore, but when you have an inverse function and you take the derivative of the inverse function, it relates to 1 over the derivative of f. So that's why it makes sense that if you have a problem that is ill-conditioned, then you consider the inverse problem of that. That looks like differentiation versus integration. The inverse problem will be well-conditioned because you're basically taking the reciprocal of a condition number.
The third inequality.
From here to here?
Yes.
Okay. So, if you think of this integral as like area under a curve. So, the area of this region has to be less than or equal to the area of a rectangle that has the same width as this region, b minus a, and the height would be the maximum height of the region. All right, so any questions about what happened here for conditioning? Okay, now we get to specific interpolatory quadruples. These are called Newton-Cotes rules. Although I think they were actually invented entirely by Cotes. Not really sure what role Newton played in this. How most students mathematicians get their name put on stuff, but it had nothing to do with it. My favorite example of that is Gaussian elimination. Gauss did not invent Gaussian elimination. But whatever. Okay, so the trademark of Newton-Cotes rules is that your nodes are chosen to be equally spaced within the interval AB. I'm going to start a new page. Okay. Now there are two types of Newton-Cotes rules. One is closed rules. In that case, the endpoints A and B are included among the nodes. And then you have open rules that do not include A and B. So the simplest Newton-Cotes rule only has one node in it. It's called the midpoint rule. So you select your one node to be the midpoint of the interval AB. And that node has one weight to go with it. That's just the width of the interval, B minus A. So then what you're doing is you're approximating your integrand f of x by an interpolating polynomial of degree 0. In other words, a constant function. Because remember, however many nodes you have, you're approximating f by an interpolating polynomial of degree 1 less. So in that case, that would be degree 0. So it's just f at the midpoint. So this is the whole quadrature rule right here. That you're taking, you're approximating the area under a curve by the area of a rectangle. The width of the rectangle is b minus a, the width of your interval. And then the height is given by the value of f at the midpoint. Now, because the only node is the midpoint of the interval, so the nodes do not include A and B. This is called an open Newton-Cotes rule. And the degree of accuracy is 1. So remember I said earlier, if you have an endpoint rule, the degree of accuracy is at least n minus 1. Well, that would be 0 in this case. So in this case, the degree of accuracy exceeds the lower bound. And the reason why is, if you evaluate f at the midpoint, if f is a linear function, it will get the exact result. Because if you're taking the value of f at the midpoint, and it's and function f is a line, then okay, you're gonna have error on to the left of the midpoint, error to the right of the endpoint, but the errors will cancel, and that's why you'll get the exact result. Questions about midpoint rule? Next, trapezoidal rule. So here we have two nodes, and the nodes are just the endpoints, A and B. So that's an example of a closed rule. So these two nodes have two weights that go with them, and they're both equal to b minus a over 2. So what you're doing is you're approximating f by a linear function. It's this one right here. Here it's written in Lagrange form, and then here I've written it in point slope form. So it's a line. Actually, yeah, it's a secant line that passes through graph of f at x equals a and x equals b. So this is what the trapezoidal rule looks like. So you're approximating the area under the curve f of x with the area of a trapezoid. The width is b minus a, and then the heights are values of f at the endpoint, f of a and f of b. So much more accurate than a Riemann sum. And this has degree of accuracy also 1. So it'll handle linear functions exactly, but nothing higher degree than that. Finally, Simpson's rule. The Simpson's rule is also closed. It has 3 nodes. Those nodes are A and B, the endpoints, and also the midpoint. So in fact, it's the union of the nodes from the trapezoidal rule and the midpoint rule. Okay. Now, for convenience, I've defined the midpoint and defined M to be the midpoint. Now, since we have 3 nodes, we have 3 weights, but they're not equal. So the weights for the endpoints are equal to b minus a over 6, but the weight for the midpoint is 4 times as much, so it's 2/3 times b minus a. That's what we see down here. This is Simpson's rule, and here it's easy to see that the much more weight is assigned to the mid value of f at the midpoint, 4 times as much as the other endpoint. But you wouldn't expect, you might think that all the weights should be equal. So in this case, f is approximated by a quadratic polynomial, and here it is in Lagrange form, admittedly kind of a mess. So because it's being approximated by quadratic, then you would expect that this Simpson's rule would integrate polynomials of degree up to 2 exactly. But we can actually do better. The degree of accuracy is 3. So even though we're using a quadratic approximation, Simpson's rule will integrate up to q base exactly. It's also worth mentioning that the Simpson's rule can be thought of as a linear combination of the trapezoidal rule and the midpoint rule. So 1/3 times the trapezoidal rule plus 2/3 times the midpoint rule. So it's an unequal linear combination. So those are the 3 best known Newton-Cotes rules. They have 1 node, 2 nodes, 2 nodes, and 3 nodes. Questions about any of these? Now, how accurate are they? So I said earlier that the approximation of the integral is the integral of the approximation, which in this case is a polynomial of some degree. So from that, we can conclude that the error in the integral is the integral of the error. In other words, to get the error in any of these quadrant rules, since in all cases we're approximating the integrand by a polynomial, to get the error in that approximation, we just have to integrate the polynomial interpolation error. So I'll show you what that means for a trapezoidal rule. So a trapezoidal rule, we're approximating the integral of f by an integral of this first degree polynomial that I showed you earlier that interpolates f at the endpoints a and b. So, well, the integral of f minus p1 is the interpolation error, and we know what that is. This is from a theorem from the error analysis section in chapter 7. So I applied that theorem with n equal to 1, and interpolation points a and b, and this is what we have. So here we already have an expression for the error, although it's not a very nice one. We can get a simpler form of the error than this. And the way I'm going to do that is by using a theorem from calculus. You may have seen this in Cal 2. And honestly, I remember telling you how one of my own professors told me that he labeled Taylor's theorem as a fundamental theorem of numerical analysis. But I think this is a good candidate for that distinction also, the weighted mean value theorem for integrals. Actually, I don't know if I can state it here. Okay. I'm going to tell you about mean value theorems first, and then I'm going to circle back around and do this. This is a mean value theorem that you're most likely to remember from Cal 1. Mean value theorem for derivatives. That this quantity here is the slope of a secant line, that would b minus f of a over b minus a. That is exactly equal to the derivative at some point c between a and b, an unknown point. This leads to these really, in my opinion, stupid problems they assign in Cal 1 classes everywhere. All the calculus textbooks have them, where we give you some function s, interval a, b, and they say, find the point c at which we have equality here. Like, that's totally not the point of the mean value theorem. The point is that such a point exists. Most cases, you're never going to be able to find it. So, stop it. Okay, so that's one for derivatives. Now, we can use this theorem to get what's called a mean value theorem for integrals. So now, I think of my function f as being the antiderivative of some function g. So that f of b minus f of a is equal to, that's equal to the integral of this derivative g. But that is equal to the derivative at a select point times b minus a by the mean value theorem for derivatives. But here we have the mean value theorem for integrals, that the integral of a function g from a to b is equal to b minus a times the value of the integrand at some point c. Now, we have a more general theorem that's needed, that we're going to need. This is the weighted mean value theorem for integrals. So if you have the integral of fx times g of x, and if you know that g of x does not change sign on the interval ab, then what you can do is you can pull f out of the integral where it's evaluated at an unknown point c. G of x stays inside the integral. So then, because what if this integral is too difficult to work out, but this integral can be worked out? Then you have an approximation of your original integral. So this is the theorem that I'm going to use to get a nicer expression for the error in the trapezoidal rule. But first, any questions about these mean value theorems? Okay. So right now, this is the expression I have for the error in the trapezoidal rule. So what I do is I apply the weighted mean value theorem for integrals, because this quantity here, x minus a times x minus b, where is this equal to 0? Only at a and b. But those are the endpoints. So this whole expression is less than or equal to 0 on ab. In other words, on ab, it does not change sign. So I'm allowed to use a weighted mean value theorem for integrals. I can leave the x minus a, x minus b in there, and I pull out the rest of it, f double prime, evaluated at some unknown point, divided by 2. So now that I have this for my error, this integral can be evaluated. Because it doesn't depend on f, it doesn't depend on anything that's unknown. So I handle that down here. So I have this integral of x minus a, x minus b. And what I do is I make a u substitution. U is equal to x minus a over b minus a. That maps the interval ab to the interval 0 to 1. So now we have this integral to evaluate that has this factor outside of b minus a cubed. So then I evaluate that, and this is what I get. final result is minus b minus a cubed over 6. So now, to get the overall error formula, I take this quantity, minus b minus a cubed over 6, and I multiply it by the second derivative at an unknown point over 2 that I had earlier. So this is the whole thing. So it's minus second derivative at an unknown point in AB over 12 times b minus a cubed. So that's the error in the trapezoidal rule. Any questions about getting at error formula? Now, unfortunately, for a midpoint and Simpson's rule, the exact same approach can't be used because both of those rules involve a midpoint m. So you get an expression like this, but unfortunately that does change sign in AB. So it kind of sort of can be worked around, but it's not easy. So we're not going to go through that here. But here are the error formulas for a midpoint rule. Notice it's quite similar to one for trapezoidal rule, even though it has one less node. The error is actually a little bit less. And then because Simpson's rule uses more nodes than we have, so it also has a higher degree of accuracy. So whatever the degree of accuracy is, the order of derivative in your error is that plus 1. Because trapezoidal rule, midpoint rule, those have degree of accuracy 1. That means they're exact for all functions whose second derivative is 0. That's polynomials of degree 1. So we have a second derivative in the error formula. Simpson's rule is exact for all polynomials up to degree 3, whose fourth derivative is 0. So that's why we have a fourth derivative in the error. Also notice whatever derivative we have here, the power of b minus a is always going to be 1 greater. Okay. Now, what I've shown you are low order Newton-Cotes rules. They all have a very small number of nodes, 1, 2, and 3. Can we go further and have higher degree Newton-Cotes rules? Certainly you can. But there's one drawback to this approach, and that is at some point, as you increase the number of nodes n, you're going to start getting negative weights. So far, we did not see any negative weights, but it will happen eventually. It's been proven that for n greater than or equal to 11, there are no Newton-Cotes rules that have all positive weights. Can't happen. So you should never use those. In some cases, I guess it depends on whether the rule is open or closed. I've seen negative weights for as low as degree 8. And I guess there's probably a reason why I couldn't even tell you off the top of my head what the names of higher degree Newton-Cotes rules are, because no one bothers teaching about them. But one reason is, as we see here, the error depends on higher order derivatives of your f. And if we use more nodes, that would depend on a higher order derivative still. What if a function is badly behaved and those higher order derivatives can get quite large? So you're not really gaining anything. Now, the fact that these higher order Newton-Cotes rules don't work well and have negative weights, that's related to what I told you earlier about polynomial interpolation. How polynomial interpolation, remember, Newton-Cotes rules, the nodes are all equally spaced, and we already saw that polynomial interpolation with high degree, equally spaced points is a terrible idea. That's Runge's example. So, based on what was discussed back then, what was the workaround? Chebyshev points. And that is the thing with integration. It's called Clenshaw-Curtis quadrature rules. I won't really get into it here, but the idea behind it is that Chebyshev points are used as nodes instead of equally spaced. And they've been found to be quite effective. But it's guaranteed that no matter how large n is, you'll always have positive weights. So, because you would think that the more nodes you use, that the more accurate the integral should be. That if n goes to infinity, the approximate integral from the quadratic rule should converge to the true integral. That is only proven true if you're guaranteed to have positive weights for whatever value, no matter how large n gets. So it's like, for instance, so it can be shown that like Clenshaw-Curtis rules converge, but Newton-Cotes would not. Okay, questions about Newton-Cotes rules? I'll take a quick check here. See if, whoops, don't want that. In particular from the section that I've not talked about here. I mentioned earlier that the approach I used to show you the error formula for the trapezoidal rule that could not be applied to Simpsons or midpoint. Here's a different approach to taking the midpoint, and I can assure you it's quite ugly. But some of you might go for that sort of thing. There's one before into existence. But I thought I had an example here. Oh. No, you know what? I'm thinking about something that's in the next section. Okay. So, never mind. Okay. Well, yeah, that's all I have. But are there any homework questions?
So about exploration 7.5.1 and 7.5.3. You got it in MATLAB or on paper?
Okay.
This is done on MATLAB.
Oh, these are okay. 751 can be done in MATLAB. It does not have to be. Actually, you know what? I would recommend doing it on paper. And 752, that has to be done on paper.
What about the other explorations for that?
Which one would also go? List.
9.1, 2, 4, 6.
Okay, wait, so 9.1, but the expiration is 2, 4, 5, 6? Okay. Let's see. Okay, well, yeah, number 2 is certainly a MATLAB problem. Writing a MATLAB function. Okay. Number 4, that is on paper. 5 is, okay, that's a MATLAB problem. And number 6, okay, that is on paper. So there's a bit of a mix. Well, like I see, the majority of the problems are on paper. 4 out of 6. Okay, so does anyone have any questions about specific problems at this time?
That wasn't. Let's see. I think we want Thursday, it's not.
What?
Says it's due Thursday.
Oh, I usually make it due 1 week after I finish covering a section. I finished covering 9-1 last Thursday. But,
Let's see what you
I mean, I don't care when it's turned in, so. But look at the.
But when test time draws closer, you might care.
On test time, well, there's only one test left. That's the final. Also, the, okay, so we're up here now. And the, remember the lowest, sort of a whole collection of homeworks and quizzes, the lowest two among those are dropped. So what that means is, for example, if you decide to do all the quizzes, then the last, you could drop, you could not bother with the last two homeworks if you want.
The two lowest quizzes in the
Okay.
Yeah, so, yeah, so 10 homeworks, I think there are 9 quizzes. So, it's quite better off just doing all the quizzes.
Originally, they said.
So that can take some pressure off.
Thank you.
Yeah, because a final does not involve any MATLAB. Okay.
Once again, no MATLAB.
Okay. I guess we're packing it in. So continuous integration on Thursday.